Hey there, and welcome to this explainer. If you're a student staring down a seriously intimidating list of cybersecurity terms right now, you are absolutely in the right place. Today, we're going to take all that heavy syllabus jargon and translate it into a clear, exciting SPICE toolkit. Because believe it or not, the concepts you're about to study aren't just dry academic requirements, they're literally the fundamental building blocks of how the entire modern world keeps its secrets. So, get ready to completely master your curriculum.
Okay, let's dive into this. We're looking at a pretty familiar site, your actual syllabus. And yeah, it looks like a whole lot of professor speak, doesn't it? You've got bullet points with these massive words like cryptography, steganography, AES, DSA, and all these different types of keys. It can honestly feel incredibly overwhelming to look at a list like this. But my goal today is to show you that this isn't just a reading list, it's a training manual. We're going to decode this exactly the way a secret agent would, turning every single one of these daunting bullet points into simple, powerful tools that you'll easily remember come exam time.
So here's our roadmap for today's mission. First up, we'll master cryptography and steganography. Second, we're going to break down AES and DSA. And finally, we'll tackle the absolute genius of public and private keys.
All right, let's jump straight into Section 1, Cryptography and Steganography, or as I like to call it, the art of keeping secrets. Now, this section is really all about the ancient foundational art of keeping things hidden. And we're going to look at two fundamentally different ways humans have evolved to do exactly that. First up is cryptography. Now, despite the really intimidating word, the core concept is pretty straightforward. It's just writing a message in a secret code. Think of Julius Caesar shifting letters around to hide his military commands from enemies. Cryptography literally scrambles your actual message. Imagine you have a highly sensitive letter. If you use cryptography, you scramble the letters and words into a totally unreadable format. The enemy might intercept your letter, they might even physically hold it in their hands, but all they're going to see is absolute gibberish. They know you sent a message, sure, but they have zero idea what it actually says.
Now contrast that with steganography. If cryptography is a scrambled code, well, steganography is basically writing your message in invisible ink. The goal here is entirely different. You aren't trying to make the message unreadable, you're trying to hide the very existence of the message in plain sight. An interceptor wouldn't even know there was a secret being passed in the first place. In our digital world, this might mean hiding a secret text file deep inside the code of a totally normal-looking picture of a cat. Nobody suspects a thing.
And this brilliantly illustrates the core contrast you need to remember for your exam. On the left, cryptography is all about changing the message. On the right, steganography is all about hiding the message. Cryptography essentially says, hey, you can see I'm talking, but you can't understand me. Steganography says, you don't even know I'm talking. Keeping that simple, distinct difference in your head will seriously make this part of the syllabus a total breeze.
Moving right along to Section 2, Understanding AES and DSA, which are our modern security tools.
So now that we know the basics, let's look at some modern algorithms. You're going to see the acronym AES a lot. It stands for Advanced Encryption Standard. But listen, don't get bogged down in the complex math just yet. Just think of AES as this massive, heavy-duty padlock on a bank vault. It's a highly specific, incredibly strong method used to encrypt your actual data. When you want to lock a file away so that absolutely no one else can read it, you throw the AES padlock on it. It is literally the gold standard for scrambling data securely today.
But here's a fascinating problem. What if I receive a locked message, and I want to be 100% sure it actually came from you, and not from some imposter pretending to be you? Well, that's where DSA comes in. DSA stands for Digital Signature Algorithm. Actually, scratch the technical definition for a second. Think of DSA like an old-school, unforgeable wax seal on a royal letter. It doesn't hide the contents of the letter at all. Instead, it mathematically proves the sender's identity and guarantees that the message hasn't been tampered with along the way.
So, the crucial point is how these two tools serve entirely different but super complementary purposes. Think of it like this. AES is your padlock. Its purpose is to encrypt data and keep it private. DSA, on the other hand, is your wax seal. Its purpose is to verify identity and keep things authentic. In the real world, digital spies and computer systems use both of these together. They lock the data down with AES and stamp it with DSA.
Now this brings us to a massive, seemingly impossible dilemma. Let's say you and I want to use that amazing AES padlock to send a secret message. Well, AES requires a shared key, meaning we both need the exact same physical key to lock and unlock that padlock. But if we're on opposite sides of the world, how on earth do I get that key to you safely across the internet without someone else intercepting it? If a hacker steals the key while I'm trying to send it to you, the padlock is basically useless. This right here is the ultimate cliffhanger of modern security.
Which leads us perfectly into Section 3, Private Key and Public Key Cryptography. Let's learn how to share secrets safely.
To solve that crazy cliffhanger of sharing keys safely, mathematicians created a system where you don't just have one key, you actually have a pair. The first part is the public key. Think of the public key like a super secure mailbox on the street with a slot in it. It is completely safe to share the location of this mailbox broadly with everyone in the world. Why? Because anyone can walk up and securely drop a letter into the slot, but once it's in the slot, they can't get it back out, and they certainly can't read what's already inside.
Then you have the second part of the pair, the private key. This is the physical, unique key that actually opens the bottom of that mailbox so you can collect and read your mail. This key must be kept strictly by the owner. You never, ever share your private key. Because you're the only one holding it, you are the sole person who can unlock and read the messages that were deposited into your public mailbox.
Let's move to encryption and see how this builds a completely secure internet. If I want to send you a secret message, I don't need to risk sending you a key at all. Instead, I just ask for your public key, your mailbox location. I drop my secret message right in. Now it's locked. Even I can't read it anymore. The message travels across the internet safely because the only way to unlock it is with your private key, which has never even left your pocket. These two distinct keys work together as an inseparable pair to secure pretty much every piece of communication we send today.
And just like that, we've decoded your syllabus. From the ancient invisible tricks of steganography to the heavy digital padlocks of AES to the brilliant two-key system that makes the whole internet possible. As you dive into your coursework this semester, just remember, you aren't just memorizing a list of acronyms for a test, you are learning the mathematical magic that secures the modern world. So, as you look at these concepts in class this week, ask yourself a question. As quantum computers threaten to shatter these algorithms in the near future, if you were designing the next great digital vault, how would you keep the keys safe? Happy studying and stay curious.